My talk today will be focused mostly on NMR methods, and I will show you how to apply them on a number of systems. I will start motivating the choice of solid-state NMR for this type of applications, and then I will go over 3 topics. One is the use of silicon-29 NMR and chemical shift in particular for the study of nano-size ZSM5. Then I will have some experiments on ethanol dehydration reaction followed by NMR using operando methods. And then I will show you a number of studies on supported palladium nanoparticles, again by NMR. Now, why do we want to use NMR in disordered solids? Well, there are, first of all, many NMR active nuclei. We don't require order. We have access to a very wide range of temperature and potentially also a wide range of pressure. We can work with air-sensitive samples, and we can use NMR for analytical purposes and perform operando studies if we have the right experimental conditions. So it's a very flexible technique. If we look at the periodic table of elements, we can see that if we don't limit ourselves to just spin 1/2 nuclei, but also include nuclei with spin larger than 1/2, which are quadrupolar, the vast majority of the periodic table will have NMR active nuclei. Many of these are actually very useful for catalysis. It's very frequent that we consider nuclei like silicon and aluminum in a zeolite, alpos, sapos, but we also have many other elements which are useful to follow reaction on organic materials like carbon, nitrogen, and so on. But as I said, the vast majority of the periodic table has access to NMR active species. So if you have a material in which you use some other metallic species for doping, chances are you could potentially do NMR on it to see the effect of doping on your material. I will not show many Hamiltonians, but just very briefly. If we work on solids, all the spin interactions will be tendentially anisotropic. And I want to discuss them very briefly because we will have to discuss all of them for the different applications we will consider. So the chemical shift is used in a liquid state NMR for a characterization purpose to verify that the synthesis has gone right, and it's a very common parameter. But the chemical shift in solid is orientation dependent, and we also have an anisotropic component, which I will discuss later for the silicon NMR application. As I said, spins which have a value larger than 1/2 have a quadrupolar moment, and that can be both a challenge, but also a wealth for information. And we will actually discuss quadrupolar nuclei in some of the experiments we did on the supported palladium nanoparticles. So I want to highlight this. Additionally, we have some interactions which involve 2 spin orders. So we can have spins talking to each other, and that can be used to probe information about proximity and so on, which again is very valuable if you want to determine structural parameters. Now, on a solid sample, if you run the experiment under static condition, it's quite common that your spectrum looks kind of broad. This is the spectrum for glycine. As soon as you start spinning, you can break the very broad line shape into spinning sideband, and if you go fast enough, you can get the isotropic peaks. That is true as long as we deal with the spin 1/2 nuclei. For quadrupolar nuclei, the situation is a lot more challenging. But I wanted to point it out for you because what we are breaking down here by changing the spin rate is some of the anisotropic components that will be discussed as part of our applications. If we want to look at it graphically, instead of formulae, we can see that isotropic interactions have a spherical nature. Anisotropic interactions can be identified with the rank 2 tensors, and you can look at them like the orbitals if you like. And while only some interactions are retained in liquids. All of these interactions are retained in solids. Now, after this very brief introduction of what we will be dealing with, the first topic I will cover today is silicon-29 chemical shift study on ZSM5. This is a particular batch of ZSM5 provided by our collaborators, and it's particularly ordered, and it's made up of nano-sized crystals. Now, there is a wealth of literature when it comes to silicon-29, and the isotropic chemical shift of silicon-29 has been reported in a number of papers. I just list a few here as a signature to establish what type of environment the silicon is, what is the coordination number, and so on. And you can relate it to the type of site or the silicon oxygen silicon angle, and so on. You can complement experimental data with the first principle calculations, and the DFT is actually very powerful to study this type of materials, and usually the consistency is pretty good. And over here are some theoretical data which correlate DFT with the experimental parameters from the Ashbrook group. These DFT calculations were done using the CASTEP software, which is the favorite approach for NMR calculations in solids. Now we want to focus on the particular ZSM5 provided by the Mintova group. And this is indicated here. We have a silicon to aluminum ratio of 40. Here is the reference for the work. On this particular type of zeolite, we also have a tiny amount of molybdenum doping with a weight percent of about 0.5%. With this small addition of molybdenum, they managed to prepare a material which healed a lot of the defects. It's virtually almost free from silanol groups. So if we look at the conventional 1D NMR spectrum, we have over here, yes, the main Q4 site for the species which don't have any aluminum nearby. And then we have a site here for the species in which there is one aluminum nearby. This is a very minor component because, as I said, we have very few aluminum in this system given the ratio of 40. Now, we decided to do further studies on this material, and we adopted a computational approach for this type of studies. So we used CASTEP again. And what we did is that we tried to compute the structure, placing aluminum in various places because we were not sure exactly where the aluminum substitution was taking place. And instead of doing the usual thing, which is just to look at the isotropic chemical shift, we decided to also have a look at what is the chemical shift anisotropy, which, as I said, is the anisotropic part of the chemical shift. And what we noted is that in a simulation, all the Q4, which don't have any aluminum nearby, had a moderately low value of the CSA, while the calculation for the chemical shift anisotropy gives a much, much larger value when we have a neighboring aluminum. And that was something not reported before. Now, these are some calculations on silicate 1 and on a ZSM5. We wanted to explore if this was actually something that we could trust, or if it was just a one-off for our system. We extended the study and shared some calculated data with other researchers, which provided us with additional chemical shift versus CSA data on other systems which had Q3 and Q2 sites. And we can see that in this particular case, even if you have Q3 or Q2 sites, you still have relatively small value of the chemical shift anisotropy, though the chemical shift axis is spread over a very wide range. So again, our silicon which is close to aluminum, has a very, very distinct signature compared with everything else. Now, up to this point, the work was exclusively computational. We thought, well, this is something we predicted. Can we actually verify it? Because otherwise, if it's just on simulation, it's not that much use. So what we did is that we used a symmetry-based recoupling sequence, which is indicated briefly R1825. We don't need to go into the technicalities, but basically, it's a sequence that reintroduces on a rotating sample some of the anisotropic interactions. In this case, it reintroduces the chemical shift anisotropy. And if you do the experiment in a two-dimensional mode, you can end up with a spectrum like this, where you have this dimension here, which is the isotropic chemical shift axis, and this dimension here, in which the peaks are separated by a quantity which relates to the chemical shift anisotropy. You cannot just read the peak position and get the value. It actually requires some simulations in order to extract it, but there is a very strict relationship between peak separation and chemical shift anisotropy. So with this in mind, we actually performed the experiments. I did show you that the spectrum was not well resolved, but if we take a slice in the area for Q4 with 0 aluminum and the area with Q4 with 1 aluminum nearby, we have the slices here, we have experiment here, and then we have the simulation here. So there are some distortion because we have a distribution of side, but it's quite clear that the match is pretty good. And so we actually verified, starting from a simulation down to experiment, that the chemical shift anisotropy can be used as a parameter to identify the silicon atoms close to the aluminum heteroatom. And now we want to explore if this can be extrapolated to different types of systems. But basically, we discovered a new dimension to explore and separate atoms near a heteroatom, which could be important in other materials. And just to mention, all the simulations here were done with the Simpson code, for those who are familiar with this type of systems. The second part of the presentation gives a flavor of what NMR can do through operando type of method. These are preliminary data that we need to wrap up a little better. But basically, we follow the ethanol dehydration reaction by solid-state NMR. And this work was done in collaboration with the Raja group some time back. And a few of the people that contributed are here, Matt. So for the ethanol dehydration reaction, why do we want to do it? Well, ethylene is the result of the ethanol dehydration reaction, and it's commonly used in a lot of plastic and polymers. We have a significant proportion of ethylene coming from cracking of hydrocarbons. And as has already been mentioned by other people before me today, who talked about ZMN5 or SAPO34, just a talk prior mine, solid-state acid catalysis for dehydration is a very powerful technique. While the conventional reaction takes place at temperatures above 350 degrees, if we actually use SAPOs for this type of purpose, we can do the reaction a lot cooler, usually in the region of 250 degrees or thereabouts. And this is the possible set of reactions taking place and leading to the process we want to follow. So it involves always starting from ethanol, but then depending on which direction the reaction goes, we can consider various rate constant to go straight to ethylene or to have a diethyl ether as an intermediate and then having that reacting further to generate ethanol. What we used for this type of application was SAPO. SAPOs are a silicon doped aluminum phosphate. Depending on the way we do the substitution, we end up with different type of materials, which will have different type of acidity, and we can end up with clustering, with the moderate strength acid site, very strong acid site, and so on. This can be actually guided depending on the type of SAPO infrastructure we work with. And as part of this work, we initially considered two types of SAPOs, SAPO 5, which has very large pores, but does not actually lead to significant amount of ethanol because the reaction usually stops predominantly here at the stage of diethyl ether, or SAPO 34, which has already been discussed earlier today, which has pore size of 3.8 angstrom. This one does not have silicon islanding as in this case, but has isolated acid sites. These acid sites are very strong, and this is ideal for the production of ethylene. For the actual experiments in the NMR equipment that we have in our university, we actually used a doped version of SAPO 34, magnesium SAPO 34. This increases further the acidity of the SAPO 34 species. And thanks to that, we could perform the reaction at a temperature which was even lower, and it was compatible with the operation of our NMR equipment. So for this type of experiment, we mixed just shy of 200 milligrams of magnesium SAPO 34 with about 10 microliters of doubly labeled ethanol. So not very much. And then we can follow how the reaction changes. I hope you're not colorblind, but in green, I indicate the ethanol, and in red, the diethyl ether. You can see that at the very beginning, we have mostly ethanol, and then as the time progresses, we start to get the peak for diethyl ether, and then at some stage, we start to get the ethylene peak coming along. Each experiment was the result of 8 scans, and it took about 2 minutes to acquire. So the data can be really acquired in real time. Then we followed the signal intensity versus time, and we could fit that to a kinetic model to extract the various rate constants. I repeated the reactions here with the associated rate constants here. And so we can clearly see that the rate constant for this process that goes straight from ethanol to ethylene is about 3 orders of magnitude lower than the others. So the reaction doesn't seem to go through this pathway very significantly. Most of it clearly goes through the step of diethyl ether, and then that progresses to ethylene. Now, the drawback of this approach in the way that it was set up by us at the time is that the NMR rotor was not entirely gas tight. So as we heat up the system to 215 degrees, if the seal is not perfect, we can have at the same time a little bit of evaporation of the samples, because at 215 degrees, both ethanol, diethyl ether, and ethylene should be gases, so they can leak. And therefore, on this plot here, we have a picture of how the overall evaporation affects the signal intensity over time. Now, these rate constants were obtained in the assumption that at that temperature, all components have the same likelihood to escape. What we aim to do next, now that the equipment is functional, is to actually repeat the whole process and follow the process at the operando, but using a magic angle spinning rotor, rotating sample in which the actual sample is completely sealed in the rotor. We did not have the equipment at the time, but now we do. The last bit of the presentation will be focused exclusively on supported palladium nanoparticles. And this work was done with Peter Wells, Chris Kilaris, Alex Goguet, Emma Gibson, and their group. And then we also collaborated with Donato De Carolis at the Catalysis Hub. Some of the experiments were performed at the National High Field Facility in Warwick. Now, supported palladium nanoparticles are important for quite a lot of applications. We can have the nanoparticle as depicted here. We work mostly on nanoparticles supported on alumina, but we can also have variation of this nanoparticle after interacting with various reagents, and we can follow these pathways to follow palladium carbide, hydride, or nitride. We try to explore not only the palladium nanoparticles, but also 3 different environments of this type. And the purpose of the presentation is to actually try to understand better what is the local structure of the substituted atom in these nanoparticles. So we will be focusing on proton NMR, carbon NMR, and nitrogen NMR. When it comes to the palladium nanoparticle for nitride and carbide, we performed a study on both these species, and we did some Xanes experiments. In this paper here, we also performed one-step calculation followed by two-step calculation to obtain the NMR parameter. One-step is a different type of simulation package also developed here in the UK, and Scalaris is one of the authors of this simulation package. And it allows to study really, really large systems. So it's very effective, but it doesn't have the NMR package in it. So the NMR calculations were transported into two-step. On these materials, as I said, after performing Xanes to check that actually the carbide and nitride were formed, we also performed NMR experiments. For the palladium nitride, we focus on nitrogen-14 NMR. Nitrogen-14 is very convenient because it has a very high natural abundance of 99.6%, but it has the drawback that is quadrupolar. So that's the property I mentioned for nuclei which have a spin larger than 1/2. And that is actually a complication, but it can also be a strength to get structural information. For carbon NMR, we have a natural abundance of the carbon-13 species of 1.1%. So that is a completely different challenge, though this is a spin 1/2. The main isotope of carbon is carbon-12, which has spin 0. So it's not that we don't observe it because of quadrupolar properties, but it's because it has no spin. So first of all, we verified the formation of the various species, the hydride, nitride, and carbide by doing the Xanes experiments. The experimental conditions for this data are reported here. And I want to mention that these samples were 1.5 weight% in palladium. So the palladium loading in the material is kind of low. On top of this low loading, we try to form, first of all, the nitride. So you can imagine that the amount of nitrogen in this really tiny amount of palladium is quite tiny. So it was very challenging to detect. What we did, first of all, was to get some reference data on a model compound. So we looked at zirconium nitride, and we performed the experiment at 9.4 Tesla. This is the main peak. Those are spinning sidebands, which are kind of artifacts due to the sample rotation. And this is in a region of chemical shift around close to 400 ppm, which is very unusual for many other nitrogen environments. So it's a clear signature for a nitride, if you like. We did manage to record a signal on our sample. That's the one here. It falls in the region expected for the nitride. But given the tiny, tiny amount of nitrogen in the system, it actually took 400,000 scans to record the spectrum, and that was a few days acquisition. So we were persistent and acquired it. Since it was such a tiny signal, we wanted to really make sure that it was not an artifact due to something else. So we recorded also a spectrum on the plain palladium nanoparticle without the nitride, and the baseline is noisy, but there is no clear signal in the nitride region. And just to make sure that there was absolutely no problem associated with the presence of metallic particle and some other strange combination, we also did an experiment of potassium bromide, which of course doesn't contain any nitrogen, and also that was flat. So this was verified to be a real signal. Now, just because we saw a signal, we cannot really say entirely what it is. So what we did is that we used CASTEP in order to estimate the quadrupolar parameter for a nitride which was interstitial and a nitride that was on the surface. Due to symmetry, a nitride which is interstitial is in a very, very high symmetry environment. And as a consequence, the quadrupolar interaction is estimated to have a size of only 6 kilohertz. If it had been a super surface nitride, the quadrupolar interaction was estimated to be 0.5 megahertz. So there is a very massive difference in estimated quadrupolar interaction, and that very significant difference actually gives a very different effect when it comes to the simulated spectrum. So over here is a very rough simulation of how the spectrum would change. If you have a quadrupolar interaction of 6 kilohertz, like for the interstitial nitride, you get a single peak with hardly any periodic peaks from the spinning sidebands. If you have a quadrupolar interaction of 0.5 megahertz for the interstitial nitride, then you get a lot of spinning sidebands which have a comparable height to the peak position of the chemical shift. And then we can use these simulations to conclude that most of the nitrogen that we actually have in our sample is actually interstitial, and that we have hardly any nitrides on the surface. When it comes to the carbide, the problem was a lot more challenging because, as I said, carbon has 1% natural abundance, so it's very difficult to detect. On top of that, while for the nitride, we had not only zirconium nitride, but also from the literature, there were a lot of species. We always had the nitrogen signal around the same region of close to 400 ppm, give or take, and also rather consistent experimental condition for a sample acquisition with a few second repetition delay. For the carbon, the situation is very different because the peak position reported for other species in literature went from about 20 ppm to 400 ppm. So it was very hard to know where we could expect a peak. And also the reported condition for the acquisition of those data was very, very challenging because some samples were acquired with a repetition delay of 9 seconds. For some other sample, they were waiting 35 minutes in between each scan. So after trying to get a signal for about 2 weeks over the Christmas break and not succeeding, we realized that we cannot detect the palladium carbide at natural abundance. Now, palladium carbide are actually important for a lot of processes, and we were very, very keen to try to determine what is the chemical shift of the carbon in this environment to actually try to utilize that for further studies. Therefore, what we tried to do was to devise a method to insert carbon-13 in the system in a way that was cost-effective in order to be able to follow it, because the applications are significant and diverse. What we decided to do was this. We made up a system in which we decided to flow in ethanol gas. Then in our tube furnace, we had a section of the furnace with SAPO 34. As we saw, during the earlier part of my presentation, but also the previous presentation, this will lead to the dehydration reaction, so we can generate in situ ethylene. Ethylene is usually used to generate the palladium carbide. So after going through this, the ethylene generated on the fly went on the supported palladium nanoparticle, and then the leftover gas went out. When it comes to conditions, our sample was 250 milligrams of a 10% palladium nanoparticle. We heated it up at 150 degrees under hydrogen. Then we placed it under a helium flow for at 250 degrees with this type of flow parameters. And then to do this reaction, we use a very controlled amount of ethanol, because of course, if you're starting to use labeled ethanol, as soon as you start putting isotopic labels, the costs are quite significant. So we only use 5 microliters of ethanol at 250 degrees. And that formed the ethylene that went to form the carbon-13 enriched palladium carbide. Now, that is what we expected to have formed. One thing is to actually put it together like that, but then it needs to be verified. So once we completed the procedure, we went to acquire the NMR data. And there we have it. These experiments were performed at the high-field facility in Warwick, 20 Tesla, so 850 megahertz magnet. And over here, we have data for the experiment over here, acquired through direct excitation. And this one here, which is the result of cross-polarization. Cross-polarization is a method that transfers the NMR signal from protons to another species. So both experiments are very consistent with the peak position here at around 163 ppm. This chemical shift is completely different from what we would expect for ethanol, but it's also completely different from the signal of ethylene. So this is clearly the product we are interested in. And this is the first experimental evidence of the palladium carbide signal, where it falls, what are the features. We don't expect the protons for cross-polarization to be in the neighborhood of the carbide itself. When we use cross-polarization, the transfer can go through space at a certain length. So it could be some protons on the alumina that contribute to the cross-polarization. We verified that this was a true signal, also verifying the way it built up with respect to time. So this is the growth of the cross-polarization signal over the contact time, which is the duration of the field on proton and carbon at the same time to transfer the polarization. And we start from a very short time in which there is a very small amount of signal, and then as time goes on, the signal builds up. The fact that there is very little signal at short time is also an indication that the protons are not very close to the carbide, which again, we wouldn't expect. We also succeeded to do a proton-carbon correlation, which is indicated here. This is the carbon dimension, this is the proton dimension. And this was the first verification of the features of the carbon-13 signal in the palladium nanoparticle. And we have several experiments that actually prove that this is indeed what we are observing. Now what we want to do further is to try to see how this carbide behaves while we use the palladium carbide with carbon-13 enrichment in various catalytic reactions. One thing I mentioned earlier when we talked about the ethanol dehydration reaction is that we had some of the sample leaking out. This is a new piece of kit that we managed to get working recently in Southampton. So on this special rotor, we can work at temperatures up to 250 degrees with up to 300 bars. And in principle, we can rotate the sample up to 10 kilohertz. And in the next few slides, we will show some results that we obtained at 6 kilohertz using hydrogen at 25 bar to actually generate the hydride of these palladium nanoparticles. Now, hydrides in NMR very often appear at negative ppm values, especially if you have the hydrides of light elements. The exact position of the peak depends on the pressure, and that has been reported, so it's a well-known fact. But actually, for palladium, there were reports of a different behavior with respect of the hydride formation. There are various forms of hydride, and the chemical shift is significantly different. There are some calculations which actually go and analyze the various contributions to the chemical shift, and they suggest that there are some relativistic effects to lead to the observed values. Since this is a new method, we needed to do some background to verify what the signal is like on a blank. So we took one of these high pressure rotor, filled it up with KBr, which is hopefully inert. And here we have the experiments for the empty rotor, KBr plus hydrogen, and then after some time when it's depressurized, and it's quite clear that we only have a single peak, and that's pure hydrogen with no significant interaction with anything. So this is our reference compound. And the baseline is due to the background of the rotor in part, because there will be protons in the plastic and the O-rings and so on. Then we decided to see what happens if we just have alumina, but without the palladium nanoparticles. And again, we get a peak for the hydrogen in a position which is quite similar. But on top of that, we also have a slight increase of the signal compared to the empty rotor. And that could be a contribution from hydroxyl and acid sites forming on the alumina. And this is not reversible because also after the pressurizing, some of these signals remain. But so far we have no evidence of any hydrides. Then we did experiments on palladium black. Now, palladium black is metallic. It's a nightmare to try to rotate it, because if you try to rotate a conductor in a magnetic field, it causes all sorts of problems. So we had palladium black, but it was diluted in KBr. We had already verified that KBr was inert. And under these conditions, we see clearly a peak for free hydrogen, but we also get peaks for the hydride, which are these two around 32 and 36 ppm. The two peaks correspond to hydrides observed immediately and after some time as the pressure goes down, because as I said, the hydride peak position is also a bit dependent on the pressure of the gas. But it's quite clear that the hydride formation on the palladium black is possible. We did the same on the palladium nanoparticle, and again, we see a clear peak in the center due to the hydrogen. We get a peak here, which is our hydride, but the peak in the center has a very different shape than what we had earlier. And we believe that due to the presence of the palladium, we have some hydrogen spillover and formation of additional amount of acid sites contributing to this signal in the position near 4 to 5 ppm. And this signal also does not disappear when we depressurize the system. So the acid sites are formed and then remain. So the conclusion is that when it comes to palladium nanoparticle, NMR proved quite powerful. We don't expect to be able to do operando using N14, given that it's so time-consuming to acquire. But the experiment on the palladium carbide don't take that long and they're very promising, so potentially they could be used for operando. N15 palladium nitride could also be an option because it would give us a boost in signal and would have many other benefits and sharper lines. We have to understand a lot more what happens with the palladium hydride, and we want to follow what happens in terms of spillover as well. Another thing that we want to consider going forward is what is the effect of considering different isotopes of hydrogen, because of course we could use deuterium, or we could use either a spin isomer of hydrogen, like differentiating ortho and parahydrogen, to see if there is anything worth studying in that direction. Thank you.
Okay, so open the discussion. Please.
I was fascinated by your palladium hydride studies because, I mean, palladium hydride's really interesting from a catalytic point of view. And have you, I mean, obviously they're quite tricky. The sort of take-home messages, it's not as easy as the carbides and the nitrides, which is a shame because I was hoping it's going to be really easy. But it isn't. But because if you have just palladium nanoparticles, you can get a lot of hydrogen into them, as you say, depending on pressure and temperature. If you alloy the nanoparticle, you can influence that quite considerably. So I'd be very interested if you could do something more on palladium hydrides, because catalytically alloying the palladium, for example, with tin, is very interesting from making hydrogen peroxide. And it would be interesting to follow that way. And the tin, it certainly influences the amount of hydride that you can form. So sorry, it's a long.
No, it's well, this is the very, very latest piece of work, because we only managed to get this piece of equipment back in operation a few weeks ago. But there is quite a lot to do, and we are ready to explore various directions. We definitely want to follow the pressure effect. We want to follow if there is any temperature effect, because all of this is happening at room temperature. And then we wouldn't be averse to actually not just look at palladium, but a mixture of different metals alloying with something else. And if it's a metal which is also easier to study by NMR, that would be great, because palladium is not really something that we'll be able to look at. But if you alloy it with something else, then we could also have the NMR side in the nanoparticle, which would be interesting. So I'm definitely open to explore that further.
There's at least half a dozen alloys.
Yeah,
I could give you.
but not all of them will be NMR friendly.
No.
So it's a matter of planning and see which features we want to highlight. But yes.
But I'll ask you at another time what the NMR friendly ones are.
Sure.
And see if they're also catalytically interesting.
Exactly.
Yeah.
Okay, I have a question for you. Thank you, Marina. Excellent talk. Again, demonstrates the applicability and the strength of the NMR for catalysis. What you have shown the cross coupling. When you, I mean, there are not only hydroxyls on the surface, but also you produce water in the reaction. So when you do the reaction,
For the carbide.
yeah, you produce water also in the reaction. Then the protons of water, and then on the surface, alumina protons could be chemically different. Then how do they affect the cross coupling?
Well, at the moment, we don't manage to distinguish very much between the different protons. We have got this data, and at the moment, all these protons, despite being at relatively high field, are not resolved well enough. So it could be that the alumina proton and the protons from water are quite close by. What we didn't have time to explore, but we want to do that afterwards in our own university, is to actually try to do the proton to aluminum correlation to break this signal and see which of these protons are actually associated with aluminum and which ones are not. So there are further studies that we can do, but they were not feasible during the visit in Warwick because it was very time limited.
Thank you.
So it's something we are thinking about.
Is there any question? If not, then really we will thank.
Thank you.